Hey everyone, class 79, our goal is to use the index of refraction to calculate the speed of light through different materials and predict refraction of light as it travels from one medium into another. So there's a little thought experiment here to start. Basically, you got a dog on the shore, there's a ball floating in the lake, and the dog is going to run to the ball and swim to the ball. And the question is, okay, well, what is the fastest route possible for the dog to take? Because we know the dog is going to run faster on land than she swims through the water. So what route is she going to take? Is it going to be a straight line? Is she going to spend more time on land? What's going to happen? Just something to think about as we move forward here. So light, much like the dog, doesn't travel at the same speed through all mediums. Light travels faster in air than it travels through water. Just like the dog travels faster as it runs on land than it swims in water. All right. Through air and space, the speed of light is 3 times 10 to the 8th meters per second. That is on your reference table. But it's slower in every other material. That's as fast as it can possibly be. The factor that determines the speed of light through different materials is known as the index of refraction. Okay, it's abbreviated with a lowercase letter n. And if you look at this chart here, these are indices of refraction for all different materials. You don't really need to worry about this frequency up top, just ignore that. What we have here is the index of refraction for all different materials. For air, it's 1, Cornell 1.47, and so on. You could check all those out. So to find the speed of light through a different medium, we use this equation n equals c over v. N is the index of refraction of that material, c is 3 times 10 to the 8th, and v is going to be the speed of light in that material, okay, which is going to be a little bit less than 3 times 10 to the 8th. What you might notice here is that when if you put in 1 for the index of refraction, v will equal c. Okay, the speed of light in air is 3 times 10 to the 8th meters per second. So let's find the speed of light in lucite. Okay, so what we are looking for is v. That is our unknown. C is going to be 3 times 10 to the 8th meters per second. And n is going to be our index of refraction of lucite, which if we look here is 1.50. So let's use n equals c over v. 1.5 equals 3 times 10 to the 8th. I'm going to leave the units out just because we have them already, over v. Multiply both sides by v, so cross multiply, and we get 1.5v equals 3 times 10 to the 8th. Divide both sides by 1.5, divide by 1.5, and you should get 2 times 10 to the 8th meters per second as your velocity. So it's still really fast, but it's considerably slower. Instead of being 300 millimeters per second, it's 200 million meters per second. So what about water? Well, we're still looking for V, and C is still going to be 3 times 10 to the 8th meters per second. And and N is going to be the index of refraction for water, which is, it looks like here, 1.33. So we use N equals C over V. 1.33 equals 3 times 10 to the 8th over V. Cross multiply. 1.33V equals 3 times 10 to the 8th. V should come out to be about 2.26 times 10 to the 8th meters per second. So we came up with the definition for refraction. It was basically this idea that light changes direction or bends. We use the word bends a lot as it goes from one medium to another. This is due to Fermat's principle. Why does this happen? It should be point A, not B. Why does this happen? Well, what you'll notice here is that when the light goes from air into glass, it takes this kind of bent, non-straight route because light will take the fastest route between points A and B. Okay, light will take the fastest route between points A and B, which is not a straight line. Okay, just like the dog, it's not a straight line because if you travel at different speeds through different mediums, then the fastest route might be a little bit different. What we came up with here is that a higher index of refraction leads to more refraction. Notice here how air going into water bends it a little bit, but going into glass, going into diamond bends it even more. We just did a couple quick examples of drawing a refracted light ray as it goes from air into water, or in reverse, from water into air. Okay, we spoke a little bit about the apparent position of the fish, where it would be located. That's not tremendously important for you to be able to recreate that aspect of it, but to realize that's why the fish tank example we saw at the beginning of class, where it looked like, when you look at the corner of a fish tank, it looks like the fish is in two different spots. That's because the light reflecting off the fish changes direction as it goes through either side of the fish tank. Okay, that's why we see it as if it's in two different places. So the fisherman isn't seeing the fish where it's actually located. He's seeing it a little bit above there, okay, at an apparent position. So what route did the dog take? It took not a straight route, but kind of like light, where it spends a little bit more time on air and a little bit less time in the water. Okay, the route's not curved either. Now, just this quick little question here: the speed of light in glycerol. Well, we know that c is going to be 3 times 10 to the 8th meters per second. V is our unknown. And glycerol, well, we got to look at our chart for that one. Let's look at it real quick. Glycerol is 1.47. So N equals C over V. I'll go a little bit quicker with this one. 1.47 equals 3 times 10 to the 8th over V. If you cross multiply, you should get a velocity that's going to be a little bit more than 2. I think it's going to be 2.04. There you have it.